Hi there, everyone. Thank you very much for joining us today for our webinar on how to design the most power-efficient products in your IoT design. IoT impacts many aspects of our lives, and today's design engineers are required to precisely and reliably measure, simulate, and model battery life cycles. But before we get started, I'd like to just let everybody know that this webinar is going to be recorded, and you'll be receiving an email afterwards with a copy of the recording, so you can go ahead and share it with anyone you think would be interested, or rewatch it if you'd like. If you're interested in any of the other webinars we'll be hosting, or to download any of the free resources we have available, such as white papers or application notes, please go ahead and visit testforce.com/academy, and you'll find everything you need right there. If during the webinar you have any questions, make sure you ask them in the Q&A section in the right side menu bar, and Wilson Lee from Tektronix will be sure to get to all of those questions as we get to the end of the presentation. I'd like to introduce Wilson Lee, Technical Marketing Manager at Tektronix. Wilson focuses heavily on design and design engineer engagement within the RF wireless, industrial power, and industrial automation markets. And now, without further ado, I'm going to hand it over to Wilson to talk about the Internet of Things.
The Internet of Things today affects all aspects of our lives in one way or another, from energy harvesting to healthcare, to transportation. Keithley Instruments solutions allow designers to precisely and reliably measure, simulate, and model battery life cycles in the presence of very small current requirements. During our webinar, we will discuss the following topics: measurement challenges on selecting and qualifying low-power components, reliably measuring power consumption, determining low battery shut-off voltage, and realistic emulation of battery discharge. It's our hope that the attendees in today's webinar will come away with a better understanding of how to properly select and qualify their low-power components, reliably measure their power consumption, and reliably profile their IoT battery. Let's get started. As a framing, the Internet of Things growth trends affect us all, from smart buildings to smart consumer homes to healthcare to industrial manufacturing. This is well represented in the graph by showing the well-recognized, fast-growing IoT applications, some including, for example, Fitbit, Nest, Amazon's Alexa, as well as the ever-growing, more mission-critical applications, which we are also seeing in telemedicine, homeland security, connected and driverless cars. Now related, there are thousands upon thousands of different devices, from wearables to implantables, security cameras, thermostats. They are all already existing or soon to be invented, which will serve this very broad market. The slide above is representing IoT's continued growth trends. And according to many industry pundits above from IHS, the Internet of Things connectivities will continue to see an exponential growth in the coming years. In fact, by year 2025, there will be an estimated 75 billion devices connected. Now, to some, even this projection may be conservative. The design-related takeaway is that even while we live in the world of digital baseband, the implication of designing in the world of IoT lives in the analog world, that being power management devices, sensors, etc., that are front and center. And in this analog world, will only be growing in scale as well as complexity. In order to squeeze battery life from your IoT device and application, the right test tools and solutions are required. This is the context and of the few key challenges which we'll address today. First and foremost, selecting and qualifying the right products for the application. Now, once the devices are selected, secondly, you will need to be able to measure your power consumption, and this will be across the device's total states of operation: power draw in sleep mode, standby, and transmit modes, where overall average current draw will need to be calculated. Third, as you choose your IoT battery, you will also need to determine the cutoff voltage. This is a difficult task, and one where you'll need to ensure that the cutoff time is correct. So as an example, too high a voltage cutoff, you will lose operating functionality. And this is all as part of mastering how battery discharge affects your end product. Lastly, how do you better measure and predictably quantify your IoT battery's life? To put things further into context of what's typically faced, a designer may be given a design requirement in the example above of a wearable BLE sensing device that would require a power budget of no more than 80 microwatts. Now, with the basis of a 4-volt lithium-ion battery, what this means is the designer will have to break down this 80 microwatts into its distinct different design blocks. So within this context, the accelerometer sensor, Bluetooth low energy RF module, the power management unit, and the microprocessor. All summed up, the designer is trying to run on a very minuscule average of 20 microamps of current. To achieve these types of power budgets, the workflow begins with the selection of low power components. This slide is representative of a typical block diagram that describes the task at hand of selecting your components. To begin with, the microcontroller are nowadays not only offering 32-bit processing power, but they're also offering ultra-low power consumption with microamps in active stage and even lower sleep mode amperage. As a designer moves from digital to analog sensors to RF transmit and receive, the underpinning theme here is that currents are running between micro to nanoamps of current. In order to properly select low power components, one has to frame the following design questions. What is the current draw at operating voltage? How much does current draw change over battery voltage decreasing? Is there a problem in evaluating any portion of the power consumption across the range of your components? And are you evaluating low power components with ultra deep sleep mode in mind? All in all, you will want to characterize their performance, and this need will be able to measure your devices at very, very low current levels. In such low current ranges which you may not have commonly worked with before. Source measure units, commonly called SMUs, bring to the table some very unique capabilities. Firstly is a versatile combination of power supply and DMM. The SMU has the unique capability to be able to source and measure, so source voltage and measure low current, and map across all 4 IV quadrants at very low currents down to the nanoamp level at which IoT devices work at. Now that we've selected our low power devices, we need to move to the second challenge, which is measuring power consumption, particularly at very small power levels. This slide is representative of the range of operating state of an IoT device, which you will observe the challenges of measurement across all the operating states, from deep sleep to transmit mode. This means measuring low sleep mode currents, tens of nanoamps to hundreds of nanoamps. This is particularly in the case of deep sleep mode, to a range of tens of microamps. Now, as your device moves from a standby to transmit mode, the need to measure transmit load currents are apparent in the tens of microamps to amps and in a super short duration of time, which could be in the milliseconds. Further, there is a need to capture the complete load current profile in order to detect unwanted transients. Such unseen and uncontrollable transients will result in higher power consumption and lower battery life. In short, to obtain the proper insights, you will want to need equipment that provides you the following: enough dynamic range for the measurement, enough sensitivity, enough speed, and sufficient memory across the entire span in which you are measuring. In practice, it's much more difficult to get the results highlighted in the previous slide. In the screenshots above, you'll see 2 measurements. The one above at the top is an IoT device being measured And the one below is current draw from a BLE device in transmit mode. There are several challenges associated with power consumption measurement, as you can see. You will see that the power consumption ranges as low as 70 nanoamps to about 29 microamps during transmit mode. Now within this waveform, you'll also note transients which are occurring within 4 microseconds. Across the span, you'll be able to better capture the load, current, performance in each of the operating states, and where you'll need design changes to keep within power budget limits. Since larger chunks of power is consumed in a transient burst of device operations, where current levels can be more than 1,000 times higher than sleep mode, any transient activity will be needed to be properly captured in order to properly debug. In summary, you will need instruments that can capture and measure current across a wide dynamic range with confidence, all the way down to sleep mode. What this means is at least 6 decades of dynamic range and 1 nanoamp or lower in terms of sensitivity. You will also need a sufficiently high sample rate and bandwidth that can resolve even the smallest detail. Thirdly, triggering options are needed, particularly if you need to correlate current measurements to specific controller actions in your design. And lastly, you'll need sufficiently large enough data buffer and storage for the millions of data points of the measurements and operating profiles, which will span across just a very few seconds. As we consider what measurement setup to use, just as a reminder that measuring the circuit's current typically adds a voltage burden to the circuit, which reduces the accuracy of the measurement. Current measurement instruments topologies deploy 2 broad approaches to measure current to shunt ammeter or a feedback ammeter. Now the shunt ammeter approach puts a resistor in the circuit and measures current by dividing voltage across the resistor. Even good conventional DMMs can add approximately 150 millivolts or more to the circuit in terms of voltage burden. So in this example, you can see that there's a lot of potential error that is added in relationship to a 4-volt lithium-ion IoT battery that we've been talking about. Overall, this approach lacks the sensitivity for many of the IoT-related applications we are talking about. Now, with respect to feedback ammeter topology, the approach here is to add an op-amp current to voltage converter. Since the voltage burden that resides on an op-amp is very small, there is not a lot of negative impact voltage burden with this approach. This also allows greater sensitivity, getting down to the femtoamp level. Lastly, as a consideration, the signal-to-noise ratio is better than the shunt ammeter approach. That all said, the only limiting factor to this feedback ammeter approach is bandwidth in relationship to the shunt ammeter approach. With the above framing, let's take a quick look at instrument options in relationship to our desired measurement needs. Let's look at the current load, current measurements with a voltage source. In this setup as depicted above, there are no voltage burdens which impact the measurement, as the measurements can be had with a current probe and a scope without having to insert anything to the device under test. As such, the current probe and a scope is almost ideal in terms of capturing current bursts and having sufficient memory for capturing a load current profile. The one important exception which is missing is the sensitivity range needed for sleep or deep sleep mode measurements. A second setup will be for scope signal capture with a large sense resistor placed within the circuit. At a high level, we see the same broad performance scorecard as in the previous setup, where we are able with the scope to have very sufficient bandwidth, sufficient sampling rate, and a number of scope triggering options, but where we cannot get below milliamps for the deep sleep mode measurements that are required. So let's look at two low current measurement options, which is depicted above, one being a Picoammeter and the other being a SourceMeter. Now, as both use feedback ammeter topology, both can attain the sensitivity range down to the picoamp level which we want. Additionally, both would provide under 200 microvolts to the voltage burden. So again, excellent. But as the chart summarizes, the meters, being primarily DC meters, cannot help us relative to the active mode current bursts, which we also need to measure. So with all these different possibilities, we're faced with a certain challenge. But fortunately, Keithley has been focused on the IoT and power measurement application for some time and has the ideal solution, which resides in a digital multimeter that has high sensitivity, measurement accuracy, speed, and deep memory. Specifically, we'll highlight the 7.5-digit DMM7510. With its unique internal topology design, it enables 1 picoamp sensitivity that definitely has enough sensitivity to measure deep sleep mode current. It also has a very low 15 millivolts of voltage burden, so low enough that will not impact the signal that we want to measure. Sampling rates are up to 1 megasamples a second that can capture all current bursts and transients. Now, the DMM7510 also has super long memory of 27 million points, which is more than enough to capture all of the operating phase data in order to optimize design, as well as look for debug opportunities where needed. The DMM7510 also has capacitive touchscreen capability, so you can see everything on a large display with pinch and zoom capability for detailed analysis without having the need to use separately a PC. Its superior accuracy, particularly as it relates to capturing sleep mode measurements, has 10 microamps range, and with a DC current accuracy of 75 ppm of reading and 30 ppm across the range. Additionally, like a good scope, it has great triggering options to review all possible current burst modes, so whether it's a rising or falling edge, as well as being able to set and use your cursors actually as a part of making your computations, all of which help, again, correlate all phases of power consumptions and measurements. Lastly, what's unique about the DMM7510 is built-in custom operations and scripting capabilities, such as TSP scripting. In all, the DMM7510 is a great sensitive measurement instrument with scope-like performance, with excellent measurement accuracy, speed, and insight to actually get us through this phase of maximizing battery life for your IoT device. We move to the third phase of our challenge, and this being assessing the battery's discharge cycle and that effect on product performance. With the challenge in mind, there are two battery characteristics which we must keep fresh in our mind. First, battery voltage decreases as battery discharges. This depends on current draw, as highlighted in the upper right chart, using a AAA battery. Internal resistance increases as battery discharges, as highlighted in the lower right-hand chart, and particularly the line marked in red. So we need to test batteries across various voltages, and what would be ideal is to be able to accurately and reliably emulate these performance points over time. Now we will model batteries as ideal voltage sources within an internal resistance, as highlighted by the image on the left side of the above screenshot. Now when your product transmits a signal, it draws maximum voltage in that very short burst of time. and the battery voltage will drop by a voltage that's equal to the change in current times the internal resistance, as highlighted in the chart on the right side of the above chart. Both open circuit voltage and internal resistance are both changing over time. And with this, you will want to determine how low the battery terminal voltage can go and how low the added voltage drop is due to current change and resistance internally, so that you can determine the optimal low battery shutoff voltage. Clearly, you don't want to set the threshold too low, which would potentially cut off periods in where you may be transmitting. On the opposite end, you don't want to set the threshold so high as to reduce the battery lifetime and efficiency. So the ideal solution is a battery simulator, a special function power supply that would emulate battery discharge as a function of decreasing voltage and increasing output resistance. And the simulator's ability to program the output resistance to then represent a battery's state of charge at any time. Now, such a battery simulator would also have fast transient response. This capability would emulate a battery's instantaneous ability to respond to a load current change. Keithley Instruments has such a specialty power supply, the 2281S Dynamic Battery Simulator. This instrument integrates a model for open circuit voltage and internal resistance as a function of state of charge. For each integral point of state of charge, the battery's model provides a 0% state of charge, fully discharged, to 100% or fully charged. And the simulation outputs a unique voltage and programs a related unique internal resistance. The state of charge is equivalent to the amp-hour capacity of the battery, and as this simulator supplies current, amp-hour capacity is calculated, representing the battery's capacity consumed. Now, as a designer, what this means is that you can efficiently get to any point of the battery simulation by setting either an open circuit voltage or a state of charge. Simply, the designer can repeatedly test, for example, an end-of-life point of the battery to determine his or her product's performance at that battery state and determine at what battery voltage the product shuts off at. We're almost there in putting the entire picture together. This final section speaks to how we can accurately and reliably know and quantify battery life. So how do we get a model that can feed the battery simulator? Firstly, we need an algorithm, one which can monitor battery voltage, discharge, and measure low current, and calculate internal resistance as the battery discharges. We also need something that creates plots similar to the screenshot above, but one in which has dynamic range in specific relationship to what your designs require. The solution is the Keithley 2450 or 2460 SourceMeter unit. The 2450 SMU, firstly, can be operated as a load, sinking constant current, and due to its current sensitivity, we can get measurements down to microamps. It also has the instrument's capability of model generating programs that can be utilized by where it discharges the battery and is taking measurement points to create the battery model that we need. The battery model can then be integrated back into 2281S for analysis and insight. So how does this all work? Well, the SMU model generating program does the following. Firstly, it monitors the battery voltage. And secondly, it creates momentary delta voltages, which creates delta current in order to measure internal resistance. It also monitors current and time to calculate amp-hour capacity. The modeling program has a number of program parameters which are programmable. Probably the most important to highlight is the ability to program discharge current. Now, the created 101 point model that the 2450 SMU is capable of consists of state of charge, open circuit voltage, and internal resistance. Tying it back to the battery simulator, the battery simulator can take the model from the SMU and then provide simulations which are highly reliable, repeatable, at varying scenarios. So as an example, you can test voltages down to very low VOC state, near the end of discharge cycle, to understand how much battery life remains as a function of time. Additionally, you could also test at any capacity of the state of charge. With the 2281S battery simulator, you can then compare different batteries which you're considering during your design development stage. You can now assess battery life in one or two prescribed approaches. You have the load current and have determined average current value. So you can determine the battery life by taking the manufacturer's specified amp hour capacity and dividing it by the average current value. Now, a more prescribed approach would be one which is more detailed and in great part has been described throughout this webinar, which is effectively taking the battery simulator and the captured load current profile in each of the operating states. You can then source your product with the simulated battery discharge curves based on the average current draw for your product. Discharge products to the product's lower battery shutoff voltage threshold. And then lastly, you can cycle your product through a usage profile. This combination of sequences will provide you the most realistic and most accurate approach to assessing your battery life. So thus far, we've talked about a great number of things coming to an optimal solution for your IoT battery test needs. We've talked about the 2450 and 2460 SourceMeter units, one in which, based on its great sensitivity and ability to measure current and voltage across 4 quadrants, allows you to qualify your low power components. We've also talked about capturing all your power requirements and profiles with the DMM7510 graphical sampling multimeter. Superior sensitivity down to a picoamp, super fast sampling at a mega samples per second, and really deep memory up to 27 million readings. All of these then can be tied together with the most realistic simulator, that being the combination battery simulator and power supply, the 2281, which can model accounts for changes both in voltage and internal resistance, and efficiently and repeatably test any state of the battery based on taking the model which is simulated from the 2450 SourceMeter unit. Before we close the webinar today, I'd like to briefly touch on the wider IoT test solutions available at Tektronix. There are multiple aspects of designing and manufacturing in the Internet of Things ecosystem. Today we've covered and focused primarily within maximizing your battery life in the IoT ecosystem. As you can see, there are multiple challenges, from wireless module selection to debugging to EMI, EMC pre-compliance to wireless standards pre-compliance, as well as navigating through the interference of things. Please come ask about the broader range of Tektronix Keithley Instruments solutions, which can help you across any of the above. The multiple design and manufacturing challenges can be seen represented in the above summary of IoT test solutions from Tektronix and Keithley. I'd like to highlight the MDO4000C, which is the only scope in the market which guarantees the RF spec given its unique ability to trigger and synchronize analog, digital, and RF. This is a great 6-in-1 instrument for all your embedded and EMI debugging needs. From an RF standards and EMI pre-compliance point of view, we have powerful yet compact USB real-time spectrum analyzers with frequency ranges up to 7.5 gigahertz, and our real-time spectrum analyzers having 40 megahertz bandwidth capture. All of these are enabled with very powerful software such as Signal View PC, as well as a newer product called EMC View, which will allow you to see all the RF standard transients in path of getting to EMI EMC test compliance. Lastly, we also have our vector signal RF generators and our range of TSG 4000 products, which rounds out our solutions for IoT test. I'd like to give a quick shout out to a new product introduction in which Keithley Instruments is very proud to announce its new DMM 6500 and related data acquisition DAC 6500 multimeters. Both have touchscreen capacitive user touch interface to simplify setups and analysis. Both have 1 megasamples per second digitizing for waveform capture as well as transient detection, multi-channel measurements, and a multiple of PC interfaces to select the optimal right interface for your needs. In relationship to today's maximizing battery life in your IoT ecosystem, but you don't need as much resolution or sensitivity as in the 7510, the DMM 6500 might be an adequate alternative. As a whole, Keithley Instruments offers a whole family of high-performance, affordable touchscreen DMMs. If more channels are needed, then the DAQ 6510 is your choice, having 80 channels of test capacity. Now, if more accuracy or sensitivity is needed, as highlighted through the webinar, you've seen the DMM 7510, which provides 7.5-digit resolution with a picoamp of sensitivity alongside with very high accuracy. All in all, Keithley Instruments is the home for your DMM needs.
Thank you for listening to our webinar on how to design the most power-efficient products in your IoT design. There was a lot of information there from Wilson, and we're just waiting for some questions to come into the Q&A box. If you have a question, feel free to type it into the Q&A section on the right-hand side of your dashboard, and we will get to answering those. Also, I'm going to post a quick poll up in the dashboard. It will be available for about 5 minutes. So while we're waiting for some questions to come in, feel free to fill in your responses there. And for those of you who attended, we will be sending out a copy of the recording so that you can watch it again later or share it with any of your colleagues who might be interested. And if you do have any questions that come up at a later point in time, don't hesitate to reach out to us at Testforce. You can reply to my email, or you can contact me easily by emailing support@testforce.com. Thank you very much for your attention and participation today. I hope that you all have a great day, and we look forward to hearing your feedback.